Welcome to Lecture 3.5, Quotients. Direct products, which we learned about in the previous lecture, make larger groups from smaller groups. You can think of it as a way to multiply groups. The opposite procedure is called taking a quotient. In some sense, it is a way to divide groups. Unlike what we did with direct products, we will first describe the quotient operation using Cayley diagrams, and then we will formalize it algebraically and explore properties of the resulting group. Here's a definition that uses Cayley diagrams. To divide a group G by one of its subgroups H, follow these steps. First, organize a Cayley diagram of G by H, and that's so we can see the subgroup H in the diagram. So you might have to add an extra generator or rearrange the nodes, but make it clear which cluster of nodes corresponds to H. Next, collapse each left coset of H into one large node, and unite those arrows that now have the same start and end nodes. This forms a new diagram with fewer nodes and arrows. If, and only if, the resulting diagram is a Cayley diagram of a group, then you have obtained the quotient group of G by H. And we write it like this, and we say G mod H. If not, in other words, if the resulting diagram is not a Cayley diagram, like maybe it has two outgoing arrows of the same color, then G cannot be divided by H. Let's do an example right away. So consider the group Z6, which is abelian, so every subgroup is normal, and consider the subgroup generated by 2. In other words, these three elements here, 0, 2, and 4. There are two left cosets, H itself, and then 1 plus H, and these things together partition the group. Note that these are also right cosets because the subgroup is normal. Now, let me show you in pictures what those three steps in the previous slide look like. So we want to take the quotient of Z6 by the subgroup H, and so we first organize the Cayley diagram by this subgroup. So here is the subgroup right here. Now note that we did not have to organize the Cayley diagram this way. Perhaps the most natural way to organize the Cayley diagram of Z6 is in a hexagon like this. This is 0, 1, 2, 3, 4, and 5. But if we do that, then the subgroup H is not organized together. It's scattered right here. So instead, we use this presentation for a Cayley diagram. Here's H, and here's this left coset, or its other left coset. Next, we collapse each left coset of H into one large node. So here's one coset of H. This becomes a node, and here's the other one. So everything inside it just gets shrinked to nothing. So these red arrows go away. And then we unite the arrows that now have the same start and end nodes. So these three blue arrows get united into one. And here's the resulting diagram. These large nodes, these coset nodes, become single vertices. One of them is H, and one of them is 1 plus H. In this example, the resulting diagram right here is the Cayley diagram. So we can divide Z6 by the subgroup H, and we see that Z6 mod H is isomorphic to Z2. And that's because this diagram is a Cayley diagram for the group Z2. We write this as Z6 mod H is isomorphic to Z2. Okay, a few remarks. Step 3 of the definition says if the new diagram is the Cayley diagram. Sometimes it won't be, in which case there is no quotient. The elements of G mod H are the cosets. Asking if the quotient G mod H exists amounts to asking if the set of left, or if you prefer right, cosets of H forms a group. More on this later. In light of this, given any subgroup H of G, I don't care if it's normal, I don't care if the quotient exists, we can still notationally write the set of left cosets of H in G as G mod H as a set, even if the quotient doesn't actually exist. Next remark. If G is a direct product, A cross B, and we divide G by A, and by this I technically mean divide G by A cross the identity, then the resulting quotient group is B. We'll see why shortly, although for now this should make sense because the quotient process sort of undoes what we did when we were constructing a direct product using Cayley diagrams in the last lecture. Although one caveat, the converse of the previous statement is generally not true. That is, if G mod H is a group, then that does not mean that G is a direct product of H and G mod H. And we'll see an example of this shortly. Let's do another example. So consider the group D3 and its normal subgroup H generated by R. So this of course is isomorphic to C3, so we casually say that C3 is a subgroup of D3, though we know that that just means that D3 has a subgroup isomorphic to C3. There are two left cosets, H itself and FH. So subgroup H, these are the rotations, and then the three reflections. So let's do the same process of taking a quotient that we did with Z6 a couple slides earlier. So let's arrange the Cayley diagram by the subgroup H. So this is laid out a little differently than we usually do it, but here you can see that this is the subgroup H, and this is the other left coset. Next, we collapse each left coset of H into one large node. Here's one of those nodes. Here's the other node. All of the red edges inside get swallowed up, and then we unite those arrows that have the same start and end node. So these three arrows all get united into one. And here is the resulting diagram. The result is indeed a Cayley diagram for C2 or Z2, whichever one you prefer. Thus, D3 mod H is isomorphic to C2. However, the direct product of C3, this is what H is isomorphic to, and C2, this is what G mod H is isomorphic to, is not isomorphic to D3. Why is that? Well, there's a lot of reasons. One simple reason is that C3 cross C2 is abelian and D3 is not. And in fact, what you get if you take this direct product is you get the original diagram, except these blue arrows are uncrossed. So the moral here is when you do things like take a quotient, you lose critical information. Like once you get down here, then you want to undo that, you can't really tell whether you started from D3 like you do in this diagram or whether you started from Z3 like you did 2 slides ago. Let's do a more complicated example now. So remember the alternating groups a number of lectures ago? To refresh your memory, the symmetric group Sn consisted of the n factorial permutations of the numbers 1 up to n. So that was a group of size n factorial. And then the alternating group, An, consisted of precisely half of those permutations, namely the ones that were the even permutations. So we actually saw the Cayley diagram of A4, this thing here, but arranged differently when we first learned about alternating groups. I think it was the skeleton of like a truncated Platonic solid. Does that ring a bell? I think it was actually several Platonic solids truncated could be arranged in a Cayley diagram of A4. Well, here's a different way to arrange it. And I have not labeled the nodes this time with permutations. Instead, I've done it just with letters because it's a little bit simpler. But notice there is some consistency here. So if there's an A and there's an A squared. So if I do A twice, I get A squared. Here's B. B is blue red. Let's do that twice. B squared is blue, red, blue, red. That indeed is B squared. And I encourage you to check that the other nodes, C and D, in fact, have the same property. So let's just check D. So blue, red, blue is D. Let's do that again. Blue, red, blue, there is D squared. And then there are these three nodes that don't have squareds in them, X, Z, and Y. I claim because they are, well, they have order 2. So let's check this with, well, of course, X squared is the identity, and I encourage you to check that Y squared and Z squared are also the identity. So in that case, these four nodes, turns out that they form a subgroup of order 4 isomorphic to the Klein 4 group. And just to further motivate this, let me actually write out what the elements of AN actually are in cycle notation. So let's see. There's the identity element, E, and there's one of those. Now there are permutations of the following form: 1, 2, and 3, 4. So these are products of two cycles, transpositions, and you can count how many elements. Well, of course, this is an even permutation because it's a product of two transpositions, and there are 3 of these. So you can have 1, 2, 1, 3, or 1, 4, and then the other transposition is fixed. So there are going to be 3 of those transpositions, and I claim that these 3 elements are precisely X, Y, and Z. And then finally, what else is there in A4? Well, there are 3 cycles. 1, 2, 3. That's one of them. Now, how many 3 cycles are there? Let's try to count them. Let's see. There is so there's one choice of what element to omit. In this case, we are omitting 4. So that's 4 different things we can omit. And then for each choice here, there are 2 3 cycles, either 1, 2, 3, or its inverse, which is 1, 3, 2. So together that gives us 8 elements. And you can check that this, add this up, you get 12 elements. So A4 consists of the identity element E, these 3 products of 2 cycles, X, Y, Z, and these 3, or not these 3, these 8 3 cycles, 1, 2, 3. And it doesn't matter too much which one you pick to be X and which one you pick to be A. I claim that you can actually freely pick any one of these 3 cycles, declare it to be X, pick any one of, sorry, not 3 cycles, any one of these products of 2 cycles, declare it to be X, any one of these 8 3 cycles, declare it to be A, and then you can fill out the rest of the diagram freely, and it works. And you'll do this on the homework. Okay, so let's erase that scratch work, and let's consider the subgroup H of V4 consisting of X, Y, Z, and E. So again, these elements of order 2 with the identity. So this subgroup is not visually obvious in the Cayley diagram. So to make it visually obvious, let's add Z to the generating set and consider the resulting Cayley diagram. So here's a picture of it. If we had Z and we rearrange the nodes, here is the subgroup H, and here are its 2 other left cosets. Next, we collapse each left coset of H into a single large node. So all of the blue and green edges get swallowed up in the middle. And then we unite those arrows that now have the same start and end nodes. So there's a bunch of red arrows starting from this supernode, going to this supernode, a bunch going from here to here, and a bunch going from here to here. And there is the resulting diagram. This resulting diagram is indeed a Cayley diagram, and it's one for the group C3. Therefore, A4 mod H is isomorphic to C3. And of course, A4, which is non-abelian, is not isomorphic to the direct product V4 cross C3, because for one reason, that has to be abelian. So let's do another example with this group, A4, but I'm going to try to divide it by a different group, and it's going to fail. So consider the subgroup generated by A in A4. So that's this subgroup right here of these three elements. And let me ask you first, do you see what will go wrong if we try to divide A4 by this subgroup? I'll give you a moment to think about it. Well, let's try it now. So here is this diagram arranged nicely by this subgroup. So it doesn't matter which one of these we call H. Let's just say H is on top. I don't need to label the nodes. Next, we collapse each left coset of H into one large node. So here are those nodes right here. This swallows all of the red arrows. And then we unite those arrows that now have the same start and end nodes. Actually, in this case, we don't have to do that because there aren't any. Previously, we always had some pair of two large nodes, in which case there were like two arrows of the same color that went between them, but we don't have that here. So let's collapse the cosets into single nodes, and we get this diagram on the right. Now this diagram is not a Cayley diagram. There are multiple outgoing blue arrows from each node. That is not allowed in a Cayley diagram. You can only have one arrow of each color going out of each node. That's because groups have that deterministic property. Every action is deterministic. So what does this mean? This means that we cannot take the quotient of G by this subgroup H. Now that we've seen examples of when the quotient process fails and when it works, let's try to understand the difference between these two cases. So here is the most recent example of the group A4 and the subgroup generated by A. So that's this let's say it's this subgroup up here. So the left cosets of H are easy to spot. There are these clusters that are at the corners of this diagram. On the other hand, the right cosets of H are not the same as the left cosets. This is because the blue arrows out of any single coset scatter the nodes. Let's look into this in more detail. So let's say this is the subgroup H. So let's say that this is the identity, and that's going to be A, and this down here is going to be X. So up here, this is H. And down here, this is the left coset X, H. Let's look at the right coset, HX. So what does that look like? For this, I'm going to use a different color. So the right coset is what you get. Let's see if this is going to come out. HX. So that's what you get when you follow the arrows in H and then apply X, as opposed to the left coset, which is when you first apply X. So you start the identity, you apply X, and then you follow the H arrows. You get this cluster. On the other hand, here you are first following the H arrows. So you start here and you follow the H arrows, you get this cluster, and then you apply X. That gets you to this node, to that node, and to that node. In other words, it gets you there, there, and there. So that is the right coset, HX. And you can actually check that the only coset that is both a left coset and a right coset is the one that always is H. In other words, all three of the other left cosets as right cosets are different. So in other words, H is not a normal subgroup in A4. If we took the time to check our first three examples, that is, I think Z6 was one of them, D3, and also we had an example with A4, but a different subgroup, we would find that in each case, the left cosets and the right cosets coincided. In those examples, the quotient G mod H existed, and H was a normal subgroup in G. However, these four examples do not constitute a proof. They only provide evidence that our claim is true. But we'll take it as a conjecture for now. Let's try to gain more insight. Consider a group G with a subgroup H. Recall that each left coset, GH, is the set of nodes that the H arrows can reach from G. So this looks like a copy of H, but at a different node in the diagram. So using the previous example, so there was X, and then we followed the H nodes. So this was XH, and then up here we have just H. So the left coset looks like identical copies of the subgroup, and each right coset is a set of nodes that the G arrows can reach from H. So we start with all of the nodes in H, and then we apply X, and we end up getting these three nodes, here, here, and here, and that is the right coset, HX. Okay, now I'm going to erase this pretty picture I made, and I'm going to show you another picture which depicts the potential ambiguity that may arise when cosets are collapsed in the sense of our quotient definition. Let's suppose we have a left coset, G1H, and we have blue arrows that go from this coset to multiple different left cosets. Then when we collapse these cosets, we get ambiguous blue arrows. In other words, we get an arrow going from this node to two different nodes, and that's not allowed in a Cayley diagram. However, if all of the blue arrows from G1H, this coset, go into the same coset, then there's no problem. When we collapse the cosets, then we have unambiguous blue arrows. In other words, only one arrow leaving this coset going to a unique coset down here. The action of the blue arrows above illustrates multiplication of a left coset on the right by some element. That is, the picture shows how left and right cosets interact. So let's go back up to here to try to understand this better. So the left cosets correspond to these big bubbles down here, but the right coset is a set of nodes that the G arrows can reach from H or from some other coset, which is an identical copy. So in other words, a right coset in this picture is going to correspond to what we get when we follow these blue arrows from one particular coset. Well, let's suppose this is not G1H, but this is just the actual subgroup. And then if we follow the blue arrows, we get down here, and this is the right coset. So this ambiguity happens precisely when the left cosets and the right cosets do not agree. However, in this picture, let's suppose this is not a coset, but the actual subgroup H. This is the left coset, that's the left coset, but the right coset happens to agree with the left coset, and there we don't get any ambiguity, and the quotient process works. To summarize, we saw in pictures in the previous slide, when H is normal in G, then every left coset is also a right coset. In this case, to whichever coset one G arrow leads from H, that is the left coset, all G arrows lead unanimously and unambiguously because it is also a right coset. So that corresponded to that rightmost picture in the previous slide. Thus, in this case, collapsing the cosets is a well-defined operation. Finally, we have an answer to our original question of when we can take a quotient. So let's call this the Quotient Theorem. If H is a subgroup of G, then the quotient group can be constructed if and only if H is a normal subgroup of G. Now remember, everything we've done so far is purely in terms of Cayley diagrams, and we will formalize this all algebraically later. To summarize our visual argument, the quotient process succeeds if and only if the resulting diagram is a valid Cayley diagram. Nearly all aspects of valid Cayley diagrams are guaranteed by the quotient process. Every node has exactly one incoming and outgoing edge of each color because H is a normal subgroup of G. The diagram is regular too. Though this argument is intuitive and quite convincing, or hopefully it is, this argument isn't quite a formal proof. We'll do a rigorous algebraic proof next. To prove the quotient theorem, we need to describe the quotient process algebraically, not just in terms of Cayley diagrams. Because even though that all made sense, when I say things like, oh, the diagram is definitely regular, I know, how do you prove that? It seems like it should be, but it's not a formal argument. So recall that even if H is not normal in G, we can still denote the set of left cosets of H in G by this notation. And I'm going to say G mod H as well, just the set of left cosets. So the quotient theorem restated algebraically says when H is a normal subgroup of G, the set of left cosets forms a group. Now that should make sense as to why that's the algebraic version of our visual argument, because when we take the quotient process, we get a Cayley diagram, and the nodes are the left cosets. In other words, the elements of this set. But there's more that we have to understand. When I say that the set of cosets forms a group, well, that means that there is a well-defined binary operation on the set of cosets. But what does it mean to multiply two cosets? Well, here's the answer. If AH and BH are left cosets, then define their product AH times BH to be, well, you want to guess? If so, you better pause the video right now, because I'm just about to tell you. Okay, so this is defined to be ABH. Clearly, the set of left cosets is closed under this operation. In other words, if you multiply two left cosets together, you will get another left coset. However, we also need to verify that this definition is well defined. And this is a subtle concept that is important and often gets swept under the rug in an undergraduate math course. So when I say well defined, what do I mean? I mean that it does not depend on our choice of coset representative. In other words, these things are two cosets. Think of them as those big, so this is AH and this is BH, as those big blobs of nodes in those pictures that we saw earlier. And one of these dots in here happens to be A, and one of these over here happens to be B. So when I multiply these two cosets together, I close my eyes and I pick an element A as a representative. Any one of these red dots will do. And I pick an element B as a representative over here. And I use that specific choice to multiply these together to get this left coset. Now you may do something differently. You might go over here and pick this red dot and call this A prime. And you might go over here and pick this this red dot and call that one B prime. And then you might say, well, the product of this coset and that coset is A prime H times B prime H, and that gives you A prime B prime H. Now we just got two different answers. I got ABH and I got A prime B prime H because we both made choices that are valid, they're perfectly valid. And this definition only works if our answers are the same. In other words, if what we get over here is A, B, H, that better be the same as, oh, maybe I should have written that over there, as A prime B prime H. In other words, somewhere up here there's an element A, B, and also there's an element A prime B prime. So in other words, to be well defined, that means it does not depend on the fact that I used A and B as representatives and you used A prime and B prime. We both better get the the same coset. And this, of course, is not supposed to be any bigger than these two things here. They're the same number of elements. They're both cosets. I just drew it bigger because I knew I had to fit in more letters inside. Let's formalize what we just outlined in that argument in the previous slide. So suppose H is a subgroup of G. Then I claim that multiplication of cosets is well defined. Now instead of using A and A prime and B and B prime, I'm going to use A1 and A2 and B1 and B2. So in other words, if we have two different ways to write the same coset, A1H is A2H, and two different ways to write this coset, let's suppose I chose A1 and B1, then when I take the product, A1H times B1H better be equal to A2H times B2H. This is how you chose to multiply those together. So let's prove this. So let's suppose that H is normal, and we have this, so the same assumptions as before. Then A1H times B1H is A1B1H, and that's purely by definition. So let's think about what to do next. So I'm going to put, if I put parentheses here, then I can replace B1H with B2H. So let's do that. So that's equal to A1B2H, and that's again by this assumption. So what's going to come next? Well, let's take B2H and let's write this as HB2. In other words, we can move the B2 over to the right hand side because H is normal. Here's what I get when I do that. So I move B2 over there, and then I regroup and I get this. So again, that's because this left coset equals that right coset by normality of H. Now next, there's several things that I could do. I could take this and I could move A1 over to the right hand side because H is normal and that left coset equals that right coset. Or I could take this and replace it with A2H by assumption. And it's not clear which one of those might work best, so you might want to try them both, and you realize that one of them gets you stuck and one of them doesn't. But I'll show you which one I chose. I'm going to replace A1H with A2H, again by assumption of this equality. And now I'm almost done. So what can I do next? Well, I can move A2 to the right hand side because H is normal. But here's something better. I can move B2 back to the left side. That's actually what we want. In other words, this is equal to A2 B2H because H is normal. We can pass elements through it. And that is the definition of the product of the cosets A2H and B2H. And that's exactly what we wanted to show. That if I chose representatives A1 and B1 to multiply the cosets together, I get exactly the same thing as what you got if you chose A2 and B2. Thus, the binary operation on the set of left cosets, G mod H, is indeed well defined. Let's return to the quotient theorem now and restate it algebraically. Remember, the quotient theorem said that we can take the quotient when the subgroup is normal. So algebraically, that means when H is a normal subgroup, the set of cosets forms a group. We did the hard part first. We showed that there is indeed a well-defined binary operation on the set of left, or equivalently right, cosets. These things are just sets, or subsets, and it doesn't matter if we call them left or right cosets. Here's that operation. AH times BH is just ABH. So all we have to do now is verify the three remaining properties of a group. What's the identity element? Well, the coset H, or if you prefer E times H, is the identity, because for any other coset, the product of that coset and H is just AEH, which is AH. And of course, we can do that in the other order. We can write that as EAH, which is H times AH. So this takes or plays the role of the identity. What about inverses? Well, I claim that given a coset AH, its inverse is A inverse H. And why is that true? Well, look what happens when you multiply these things together. You get A inverse times H, or just the identity times H. And of course, I could have done this in reverse order, like that. Now finally, what's the last thing we have to check? Closure. And this is immediate, because if you multiply two left cosets in this manner, you get this, which of course is another left coset in G mod H. So that's the end of the proof. I want to finish with a question whose answer might surprise you. So if H and K are subgroups of a group G, and they're isomorphic, then is it true that the quotients G mod H and G mod K are isomorphic? Seems like this is plausible, because with numbers, of course, this is true. If we have two numbers that are the same and we divide by them, well then we get the same number. But in fact, this is false. And here's an example that illustrates this. Here's a Cayley diagram for the group Z4 cross Z2, right here. It is visually obvious that the quotient of this group by the subgroup generated by 0, 1, so this thing right here, is the group Z4. You can see that, right? So just make each of these large nodes and collapse it, and you get Z4. Now the quotient of this group by a different subgroup is a little harder to see. So this subgroup here is generated by this element. So it also has size 2. So start here and do red, red, you get 2, 0, and red, red gets you back here. So this is a subgroup of size 2, and it's normal because this Cayley diagram, or this group, is abelian, so every subgroup is normal. We can always take quotients. Algebraically, it consists of the following 4 cosets. This is just the identity coset, and here are 3 others. And to make this clear, let me go back to the Cayley diagram. So this here consists of these 2 nodes. What next? Let me pick a different color. How about green? This coset is what you get when you start with this subgroup and apply the element 1, 0, which is the red arrow. So that's going to be, that's going to be this and this. Now this coset is what you get when you start with the subgroup and apply 0, 1, the blue arrow. That's going to be down here. And then finally, you need to pick a 4th color. This subgroup, oh, I forgot to underline this. This subgroup is what you get when you start with, not subgroup, coset, sorry. When you start with the subgroup and you apply 1, 1, so that's this and this. So that's going to be this thing here. Okay, so the 4 cosets are these, and these form a group. And what is that group isomorphic to? Hopefully it's apparent that this group is isomorphic to the Klein-4 group V4. Because what you're doing when you're adding these cosets together is you're just adding this representative together, and you have 0, 0, 1, 0, 0, 1, and 1, 1. Thus, the answer to the question above is no. Are you surprised? Well, perhaps it is surprising. And I encourage you to look for other groups where something like this happens. And in fact, you can find some good examples if you go to infinite groups. And so here's a little bit of a hint. What if G is the integers? And let's take H to be 2 times the even integers, and K to be 3Z. So the integers or the multiples of 3. Now we haven't done quotients with infinite groups yet, but I encourage you to think about what that would look like and try it algebraically and try it in terms of Cayley diagrams, both just to compare and contrast and also see which one gives you better insight. But I claim here that if you take G mod H, well, first of all, H and G are obviously isomorphic because these are infinite cyclic groups. Even though they are subsets of Z, their Cayley diagrams are isomorphic to Z. And I claim that G mod H is isomorphic to C2, and G mod K is isomorphic to C3. So I encourage you to explore this on your own and try to get some more insight.